In May 2023, Nvidia released a quarterly earnings report that shocked Wall Street. The numbers were not just good, they were so far above expectations that many investors treated the report as a once-in-a-generation moment. Nvidia's data center business was exploding, the stock jumped, and the company crossed the $1 trillion market value line. For a company that many people still thought of as a gaming graphics card maker, this was an astonishing transformation. But if you look closely, Nvidia did not become an AI giant overnight. It became one of the most important companies in the world because it spent decades preparing for a future that most people could not yet see. Nvidia's story starts with gaming, moves through graphics, scientific computing, cryptocurrency mining, and then finally arrives at artificial intelligence. Along the way, the company almost failed, made expensive bets that looked irrational at the time, and built one of the strongest software and hardware ecosystems in technology. To understand why Nvidia matters so much today, we have to go back to the beginning. Jensen Huang was born in Taiwan in 1963 and later moved to the United States. After studying engineering, he worked in the semiconductor industry, including at AMD and LSI Logic. By the time he was around 30, he and two co-founders believed that 3D graphics would become a major computing market. In 1993, they founded Nvidia. The idea was simple but ambitious: build chips dedicated to graphics computing. Today, that sounds obvious. At the time, it was not obvious at all. The early 1990s graphics market was chaotic. 3D gaming was still young. Real-time rendering was primitive. Hardware and software standards were fragmented. There were dozens of companies trying to build graphics chips, and many of them had their own way of doing things. One company might build a card that worked well with one graphics standard, only to discover that the market was moving toward another standard. Developers had to choose which hardware to support. Consumers had to guess which product would survive. The whole industry was messy. Nvidia was not the clear winner. In fact, Nvidia nearly died. In its first product, NV1, was not a major success. Its second-generation plan, NV2, never became the product the company needed. By the late 1990s, Nvidia was running out of time. The company had limited cash, cut headcount, and needed a hit product to survive. The turnaround came with Riva 128 and then Riva TNT. Those products helped Nvidia regain credibility. More importantly, Nvidia aligned itself with the direction the market was moving. It supported Microsoft's Direct 3D standard, worked closely with the PC gaming ecosystem, and improved its graphics performance at a rapid pace. This mattered because gaming was becoming more demanding. A 3D game is not just a picture. It requires a machine to calculate geometry, lighting, shadows, textures, motion, and perspective in real time. A CPU can do many things, but real-time graphics requires huge numbers of similar calculations happening at the same time. That is exactly the kind of work a graphics processor is designed to do. In 1999, Nvidia released the GeForce 256. The company called it the world's first GPU. Strictly speaking, graphics accelerators existed before GeForce 256, but GeForce 256 helped define the modern GPU category. It integrated more of the graphics pipeline into a single processor and gave Nvidia a powerful consumer brand. The GeForce name became familiar to generations of PC gamers. Around the same time, the graphics card market began to consolidate. 3DFX, once one of the most famous companies in the space, was eventually acquired by Nvidia. ATI remained a major competitor and was later acquired by AMD. Over time, the discrete GPU market became a two-company fight, Nvidia and AMD. Nvidia gradually took the stronger position. But if Nvidia had stopped there, it would have been a very successful gaming hardware company, not the company it is today. The real turning point was Nvidia's understanding that GPUs were useful for far more than games. To see why, compare a CPU and a GPU. A CPU is designed to be flexible. It is good at handling complex logic, sequential tasks, operating systems, spreadsheets, browsers, databases, and countless different workloads. A CPU is like a small number of very capable workers who can handle complicated instructions. A GPU is different. A GPU is built for parallel work. Instead of a small number of very flexible cores, it contains many smaller processing units that can perform similar calculations at the same time. That makes it excellent for graphics, because graphics is full of repetitive math. Imagine rendering a 4K video frame. You are dealing with millions of pixels. For each pixel, the computer may need to calculate color, light, shadow, reflection, texture, and motion. Then it has to do that again and again, frame after frame. That is not one complicated task. It is millions of smaller tasks that can be processed in parallel. This is why GPUs became essential for modern graphics. But the same parallel structure can also be useful in many other areas: scientific simulation, weather forecasting, drug discovery, energy exploration, engineering design, and later machine learning. The problem was that early GPUs were hard to use for general computing. They were built for graphics pipelines, not ordinary programming. If you wanted to use a GPU for non-graphics work, you needed specialized knowledge and a lot of engineering effort. For most developers, it was too difficult. Jensen Huang and Nvidia saw the opportunity. If GPUs could be made easier to program, they could become general-purpose accelerators. That idea led to CUDA. In 2006, Nvidia introduced CUDA, a platform that allowed developers to use Nvidia GPUs for general-purpose computing. This was one of the most important strategic decisions in the company's history. At the time, it did not look obviously profitable. The market for GPU computing was small. Most people still associated Nvidia with gaming. Scientific computing existed, but it was not a mass market. Building CUDA requires software investment, developer support, documentation, libraries, and long-term patience. Wall Street did not immediately reward that kind of spending, but CUDA became Nvidia's moat. Nvidia was no longer just selling chips. It was building an ecosystem. A developer could write code using CUDA, researchers could use CUDA libraries, universities could train students on Nvidia tools, companies could build workflows around Nvidia hardware and software. Once that ecosystem formed, switching became difficult. A competitor might build a good chip, but if the software tools are less mature, the libraries are weaker, the developer community is smaller, and the existing codebase is built around CUDA, the customer may still stay with Nvidia. This is the key to Nvidia's long-term advantage. Hardware matters, but hardware alone is not enough. The company built a combination of GPUs, drivers, software libraries, programming tools, developer relationships, and system-level engineering. That combination became far more powerful than any single graphics card. And for many years, Nvidia kept investing before the payoff was obvious. That is why the AI boom did not catch Nvidia unprepared. Nvidia had already spent more than a decade turning the GPU from a gaming device into a general-purpose computing platform. Before AI became the main story, however, another wave showed the world that GPUs could do more than render games. That wave was cryptocurrency mining. Bitcoin and other cryptocurrencies require large amounts of repetitive computation. Mining is essentially a race to perform calculations quickly and efficiently. GPUs were well suited for this work, especially in the earlier phases of crypto mining. During major crypto booms, demand for graphics cards surged. For Nvidia, this was both a gift and a warning. It was a gift because miners bought large numbers of GPUs, pushing demand and revenue higher. Many consumers first learned during the mining boom that graphics cards could be used for computation, not just gaming. But it was also a warning, because crypto demand was unstable. When crypto prices rose, GPU demand surged. When crypto prices fell, demand could collapse. Nvidia benefited from crypto, but mining was never the stable foundation of the company. It was a preview of GPU compute demand, not the final destination. The much bigger wave was artificial intelligence, and the foundation for that wave had been laid years earlier. In 2012, a team using a neural network called AlexNet achieved a breakthrough result in the ImageNet image recognition competition. Their system dramatically reduced error rates compared with previous approaches. The reason this mattered was not just that the model performed well. It showed that deep learning could become practical when enough compute was available. Neural networks were not a new idea. The theory had existed for decades. The problem was that training them required enormous amounts of computation and data. For a long time, the hardware was not ready. GPUs changed that. Deep learning involves huge numbers of matrix operations. These operations are highly parallel. That makes GPUs a natural fit. Once researchers saw what could happen when neural networks met GPUs, AI research began accelerating rapidly. Nvidia was in the right place because it had the right hardware, but also because it had CUDA. Researchers could actually use the GPUs. Developers could write programs. Infrastructures could be optimized. Libraries could be built. The ecosystem mattered as much as the chip. This is where Nvidia's earlier bets started to pay off. For years, CUDA had looked like a long-term investment with uncertain returns. Suddenly, it became the gateway into modern AI computing. By the time large language models arrived, Nvidia had already become the default choice for training serious AI systems. Training a modern AI model requires enormous parallel computation. GPUs are built for that kind of workload. But Nvidia was not only selling GPU chips, It was selling a full platform: hardware, CUDA, libraries, networking, servers, support, and a development ecosystem. That is why many AI companies did not simply ask, which chip is theoretically fastest? They asked, which platform can help us train and deploy models reliably? For many of them, the answer was Nvidia. This is the point where Nvidia stopped being only a graphics card company. It became an infrastructure company for the AI era.